Welcome to Hot Chips 23. Session 7, Server.
The next session is on server chips. Actually, not just server chips. We actually have a server manufacturer here, and then we have 2 server chips. The first paper, our first speaker is from a company called SeaMicro. It's a startup here in the Bay Area. Ashutosh Dhodapkar is a founder at SeaMicro. He's developed their storage and network virtualization technology. Okay, prior to SeaMicro, he was an architect at AMD, working on various x86 systems there. He has several publications in the area of adaptive architectures, holds a BSEE from IIT and a PhD from University of Wisconsin. Please welcome Ashutosh.
Thank you, Brian. Do I have to do something special here? Great. So good morning. Today I'm going to present to you some of the technology underlying the SeaMicro SM10000 family of servers. The SM10K is based on a radical rethink of server architecture, and unlike conventional servers, is based on cell phone chips. The SM10K consumes 1/4 the power and 1/4 the space of a conventional server. I'll start the talk by giving you a brief overview of the industry as well as application trends that motivated SeaMicro to rethink the way we build servers. We'll then dive deeper into the architecture and talk about 2 of our key technologies, the Interconnect Fabric and I/O virtualization. I'll end the talk by giving you a brief overview of the kind of power efficiencies that are achievable using our architecture. So as most of you already know, power is the key issue in the data center today. Power today accounts for more than 1/3 of the operational expense of a large data center. A 2007 EPA report estimated that volume servers consume about 1% of the net power draw of the country. That's more than $3 billion spent only on power in the data center. Finally, data centers are reaching the power limits, forcing them to build new ones and incurring capital expenses of hundreds of millions of dollars. As many of you might know, Apple is building a data center in North Carolina right now. That's going to cost them about $1 billion. So I think it's fair to say that reducing power not only has an economic impact, but potentially an environmental one. Now, as if the power problem in the data center was not bad enough, the application trends are making it worse. Today's internet applications are steadily moving compute to the server side. Clients are used mostly for display. Your smartphones or superphones or tablets are not just a fad, they are a trend for here to stay. These applications are all free to the users because their cost is amortized over a very large user base. However, the business hosting this application still has to pay for the data center, and thus minimizing the TCO of the data center is critical to their business. The costs in the data center are many. There's the cost of providing bandwidth, power, there's a cost of buying servers, switching equipment, storage, etc. And these applications are growing exponentially. So data centers today are facing brand new challenges around the logistics of supersize. So what are these killer apps, right? Over the last decade, academia as well as industry has been looking for the killer app. Unfortunately, there was no single killer app. Cloud's killer apps are collections of small, simple, and bursty workloads that work on big data sets, have a very high level of concurrency, and have a lot of communication between them. In the next few slides, I'm going to show you how SeaMicro's architecture was motivated by the characteristics of these applications and is purpose-built for them. At the highest level, the SM10000 is a cluster in a box with integrated compute, storage, and networking. We do that by interconnecting a very large number of cell phone class CPUs, specifically the Intel Atom, using a low latency, high bandwidth fabric. Now, unlike multi-core, which tries to do the same, we scale all system resources. Multi-cores typically scale only the compute aspect, and it's difficult to scale the I/O bandwidth. Our system provides natural scaling for compute, which is the OS threads, memory bandwidth and capacity, NICs and network bandwidth, and disk bandwidth and capacity. And as I already mentioned, it's purpose-built for cloud scalar apps. So the first choice at hand was the kind of CPU we use. Now, the SeaMicro architecture is completely agnostic to the kind of CPU we use because we virtualize PCI Express. However, for the SM10K product, we chose to go with the Intel Atom CPU, which is a cell phone class CPU, because we felt it was a very good fit for the small, simple, and bursty workloads in the data center. More importantly, using a CPU such as the Intel Atom helps us leverage the power efficiencies of scale down. The Atom has a simpler microarchitecture than, let's say, the Xeon, and that comes at a power advantage. And so I stole or adapted this graph from one of Mark Horowitz's recent works. This graph shows the energy performance Pareto optimal curves for different styles of microarchitectures, all the way from an in-order one-issue machine to an out-of-order four-way superscalar machine. Design D2 on this graph most closely represents the Intel Atom pipeline. It's an in-order two-issue pipeline. Design D4, higher up on the curve, represents what's most commonly a server class CPU, such as an Opteron or a Xeon. It's four-way issue and completely out of order. As you can see, for a 1.5x improvement in performance, design D4 consumes 2.5x the amount of power. This is the reason why server class CPUs are typically less power efficient than these scaled down CPUs. Moreover, using the Intel Atom helps us derive cost advantages because these CPUs have a very small silicon area and go in very high volume applications. So next aspect of internet apps is the high level of concurrency and communication. To address that, we took 512 of these CPUs and interconnected them using a 3D torus fabric. Our fabric is highly scalable because it's based on a distributed architecture using our proprietary ASICs. It's got very high bandwidth of 1.28 terabits per second. We designed it for a very low latency between any two nodes in the system, and the latency is typically less than 5 microseconds between any two nodes. The fabric is highly resilient because there are a multitude of paths between any two nodes, so it allows us to easily route around failures. The final piece of the puzzle is the I/O virtualization. So I/O virtualization helps us share network as well as storage I/O across all these CPUs, thereby reducing power as well as cost. Sharing I/O also helps us improve utilization of the I/O and enables new optimizations such as shared disk partitions. So the figure here shows a logical representation of the SeaMicro chassis. We have a very large number of CPUs and their associated chipsets interconnected in a 3D torus using the SeaMicro ASIC. Also connected into the fabric are the I/O cards. We have two flavors of I/O cards, the Ethernet card, which supports up to 20 gigabits per second bandwidth, and the storage card, which holds up to 8 SATA disks. And our chassis can take 8 of each of these cards. So to give you an idea of how small our compute servers are, I'm going to switch to the projector here. So this is one of our latest production boards. It's got 6 sockets of dual-core Atom processors and 24 gigabytes of DRAM. Now, to get an estimate of the size of the compute, my CEO typically likes to pull out his business card and show you that the server is the size of his business card. Now, my business card is not half as cool as his, so I got my latest acquisition, which is a Hot Wheels Ferrari. As you can see, and by the way, this is not my acquisition, it's really my son's acquisition, but I paid for it. So as you can see, each of our servers is the size of this Hot Wheels Ferrari. And just in case you think it's a big one, it's not, right? Now, these chips here are the CPUs. These 4 chips here are the SeaMicro ASICs. Now, you'll say that, hey, how come you have a heat sink on a low-power chip? Well, interestingly, the only reason we put heat sinks on there is because we're presenting at hot chips. But more importantly, we wanted to divert airflow towards the CPUs. So the chips actually run very, very cool. It's just that the airflow coming over the board needs to be diverted towards the CPUs to cool them. Now, to give you an idea of how big our ASICs are, I got one of our older boards, and I got the smallest coin that the US Mint makes, which is the US penny, not the penny, the dime. Now, as you can see, the SeaMicro ASIC is actually smaller than a dime. So hopefully that gives you an idea of the kind of density we can pack in and the kind of power advantage we have over competition. So the SeaMicro ASIC is the most replicated component of the system. So the 2 main goals while designing it was low power and extremely low cost. So we built the ASIC on a 90 nanometer TSMC technology. Per node, the ASIC is just 15 square millimeters in size. We house it in an extremely inexpensive plastic BGA package. And the ASIC is very low power, less than 1 watt per node. The ASIC implements 4 of our key features: the fabric switch, I/O virtualization. It also does clock generation for the CPU, and finally, node management. Each of our ASICs houses 2 of our nodes in the 512 3D torus. Each node has 6 fabric links, 2 in the x dimension, 2 in the y dimension, and 2 in the z dimension, to connect to surrounding nodes. These links run at 2.5 gigabit per second and use your standard SerDes. We also have a PCI Express link to the CPU. That's the primary mode of communication with the CPU. And finally, there's a crossbar to switch between these 7 links. As I've already said, the nodes are connected in an 8 by 8 by 8 3D torus, where each dimension is an 8-node loop. The torus has a very high bandwidth, 1.28 terabits per second, and very high part diversity, which helps us route around failures. In order to minimize latency, the fabric was designed to be cut through. It's also lossless and deadlock free. And finally, we separate network, storage, BIOS, and console traffic using multiple QoS levels in the fabric. So the SeaMicro ASIC presents 4 virtual devices to the CPU. There are 2 devices on the PCI Express interface and 2 on the LPC bus. The 2 devices on PCI Express are an Ethernet NIC that provides network connectivity, and a 4-port SATA HBA that provides access to 4 disks to each of our CPUs. On the LPC bus, we virtualize BIOS as well as UART. The node packetizes data coming in from these 2 interfaces and ships it over the fabric to one of the multiple shared I/O cards. All Ethernet traffic is either routed to an I/O card, specifically the Ethernet card, if the communication was meant to be with the external world, or it's directly routed to another node if the communication was internal. Disk, BIOS, as well as console traffic is all implemented on the storage card. The I/O cards connect into the 3D torus in the y dimension, and they are the primary bridge between the fabric and the I/O. They terminate fabric protocol on one side and talk to I/O devices on the other. We have 2 types of cards, the E card or the Ethernet card, which supports 8 by 1 gig links or 2 by 10 gig links. We also have an S card that holds up to 8 SATA disks. They can be either hard drives or SSDs. And it also services BIOS and console requests. Any node in our system can talk to any I/O card. So in fact, you can boot up the entire system on just one network interface and one hard drive. The I/O architecture that we use for both the storage as well as the Ethernet card is very similar. We use a hardware-software co-designed approach. We keep the boundary very flexible so that we can constantly optimize it for performance. As you might expect, all high-speed data paths are implemented in an FPGA. The control plane, which is typically more complicated, is implemented on a control plane processor. Now, we could have used hardened silicon instead of an FPGA, but the reason we went with an FPGA is because it enables us to rapidly implement features based on field requests from the customers. Moreover, the power and cost of these FPGAs is amortized over hundreds of nodes, so it's not that big a deal. This figure here shows you a physical view of the chassis. The chassis is a 10 rack unit enclosure with dual mid planes in the center. These mid planes are passive, so we designed them such that there is a very low probability of failure. The compute cards plug in on two sides of the chassis. Each side holds up to 32 compute cards. So that's a total of 64 compute cards in the system. There are 8 Ethernet cards that plug in on the back, and then 8 storage cards that plug in the front. And then the chassis can hold up to 64 disks in the enclosure. Each of our compute cards holds 4 ASICs, and each of our ASICs has 2 nodes. So that's a total of 8 nodes per C card. Each of our compute cards also holds between 4 and 6 dual-core Atom processors. That's a total of 768 cores in the system. Each of the Atom processors has access to up to 4 GB of DRAM. That's a total of 1.5 terabytes of DRAM in the system. We provide network connectivity of up to 160 gigabits per second and storage of up to 64 SATA disks inside the enclosure. We use redundant power supplies. We have 4 power supplies that plug in the top. They're 3+1 redundant. So if one of them fails, the chassis still keeps up and running on the other 3. So the last ingredient in our secret sauce is the management software. The management software implements key real-time services as well as configuration management and monitoring services. The real-time services include fabric routing algorithms, which do fault isolation and failover in the system. We have an Ethernet control plane that does IP, MAC learning, DHCP, IGMP, ARP, and various other L2 and L3 protocols. We have an integrated layer 4 load balancer, which helps us distribute TCP as well as UDP traffic onto our nodes. This integrated load balancer is a very key aspect of our system. Since this is a hot chip stock, I'm not going to go into the details. We also have an integrated terminal server, which allows us console connectivity to each of the 512 nodes in the system. And finally, we have real-time services that control the power supply, fans, etc. And all these are redundant, so there's a lot of work involved in fault monitoring and so on. On the configuration side, we have an integrated DHCP server because we didn't want to present a lot of DHCP load to the external infrastructure. We also have integrated CLI and SNMP interfaces for managing network, storage, as well as server management. And finally, we have integrated performance as well as fault monitoring tools. So to give you a flavor of the kind of power efficiencies we achieve, I'm going to show you some performance numbers here. So in this study, we compared one SeaMicro chassis to a cluster of industry standard 1RU servers. These servers were based on a dual socket quad core 2.13 gigahertz Xeon part. We put as many number of 1RU servers in the cluster as needed to match the Apache throughput of the SeaMicro chassis. The Apache bench was running on Apache 2.2, and the CPU was running CentOS 5.4. As you can see, it takes about 45 1RU servers to match the throughput of a SeaMicro chassis. Those 45 servers consume 10 kilowatts, not taking into account the power dissipated by the racktop switches, the Cyclades, terminal servers, etc. The SeaMicro server consumes 1/4 of the power at about 2.5 kilowatts. So I think it's clear that our approach brings a lot of efficiencies to the table, both in terms of power as well as space. To summarize, internet workloads are constantly moving compute to the server side, and thus minimizing power and hence TCO of data centers is critical to these businesses. The SM10K in our mind is a major step forward in this direction. It provides a 4x reduction in power as well as space. And we are shipping in volume today with up to 768 Intel Atom cores, up to 1.5 terabytes of DRAM, 160 gigabits per second network bandwidth, and 64 SATA drives. Thank you.
Mark Augustin, Samsung. Your interconnect fabric, is that built on gigabit Ethernet, or what technology are you using there?
We have our own proprietary protocol that runs on standard 2.5 gigabit per second SerDes links, but the link layer as well as higher level protocol is proprietary.
Okay. And do you use static routing for your interconnect to your IOs, or is that something that is dynamically adjusted?
So as you can see, the chassis has a lot of nodes, so we cannot use a static algorithm, because if there is any failure in the system, we need to be able to route around that. So I would say our routing algorithm is quasi-dynamic. I mean, it's not making dynamic decisions all the time, because that would dissipate a lot of power, but it's dynamic when it comes to failures.
Thank you.
Shubha Mukherjee, KVM. So you compared against Intel, which is great. I mean, the Intel Xeon server, which is great. Those margins are going to drop. But the question is, ASUS and ASUS and all those companies are already selling a few Atom servers. So, on one hand, you have this huge, massive interconnect network that seems to be binding all this. On the other side, I could connect all of them with Ethernet and still get the same low power. So have you done a comparison in terms of performance per watt and performance per cost, or performance per dollar in terms of, presumably your price is higher because you have the secret sauce with the interconnect. So how do you compare if I just took a bunch of these Atom, few core Atom boxes and then cobbled them together and created a server, or just put it in the server space?
So that's a very good question, and 4 years ago, we were thinking about this exact same question. Now, our cost is not really very high. In fact, we are price competitive with a comparable conventional server solution. The problem with interconnecting a very large number of small Atom CPUs is scaling the network and I/O. Think of connecting 512 motherboards together. Where are you going to get the 512 port racktop switch? Where are you going to get 512 disks? Where are you going to plug them in? So in fact, one of the first boxes that came out was a box from Japan, where they put 8 of these inside. But if you look inside the box, there's actually a switch there. And our interconnect was basically designed to address that scalability issue. So the power is not only in the CPU, the power is also in all the other components that go in the system.
Right, but if you look at a Google-like system, they don't, it's standard Ethernet, right? It's not proprietary InfiniBand or any interconnect. So anyway, I just wanted to understand your perspective. Thanks.
Sure.
Hello, my name is Satoshi Matsushita NEC. The latency between the node is quite low, less than 5 microseconds. Is it the user-to-user round trip time, or what is the number?
Okay, so the 5 microsecond is the worst case latency at the hardware level. Now, of course, the operating system and application times can be different based on the kind of applications you're running. At the hardware level, we have a less than 5 microsecond guarantee.
So end-to-end, the interface to interface.
Interface to interface. Yeah.
Okay. Do you provide us any special driver, user-level driver to taking the advantage?
So one of the key founding principles of the company was that we want to be able to run stock operating systems and stock applications. Absolutely no changes. And that forced us to jump through a lot of hoops, but I think we have still been able to maintain that
Thank you.
that specific philosophy.
Thank you.
Hi, Charlie Demergent, Semi-Accurate. Your individual boards have 4 of the fabric interfaces and 6 CPUs.
Right.
And the Atoms have a PCIe 1X interface.
Right.
That tells me that each chip can handle more than one lane of PCI Express.
Correct.
How many and what versions?
So each of our ASICs house 2 nodes. So on one of our current generation compute cards, we can take up to 8 PCI Express lanes. Now, if I show you one of our older generation cards, you'll see that we actually supported 8 sockets. So the amount of real estate we have on the board can hold up to 8 sockets. It's just that the specific board I showed you had 6 sockets on it.
The 8 socket versions you had used half-speed PCI Express. Can you subdivide the 1X into half-X, or does it support 2 1X lanes, and can you support 4 half-X lanes?
We support 2 1X lanes.
Okay, thanks.
I think we have time for just 2 quick questions here, and then we'll have to catch them afterward. Go ahead.
Okay. Combined question, Amitabh, Qualcomm. I noticed what percentage of your participation is in your interconnect and how much is in the CPU in the workloads that you're targeting? And I noticed that you put quotes around cell phone chip every time. Why didn't you actually go in for a cell phone chip?
Well, so when we started designing the SeaMicro server, the Intel Atom, the marketing material definitely claimed and still claims that they go all the way from smartphones to servers. So that's the reason for that specific comment. As far as the power dissipation goes, most of the power in the system is dissipated in the CPUs and the DRAM. I mean, the interconnect is extremely low power. And in fact, everything that's highly replicated that's in our hands, we made sure it was running at very, very low power.
Hi, Doug Boyle from APIC. Regarding the software, I assume you're running Linux. How many copies of Linux on the box? Is it 1 per chip, 1 per board, or what? So
it just looks like a cluster of 512 CPUs. So it runs as many copies as you would run on 512 Xeon parts. It just looks like a server. And we don't support, we don't provide the Linux. The Linux is whatever Linux you can get from the market. I don't know if I answered your question right. But in this specific instance, it would be 512 copies.
Okay, thanks.
Okay, thank you.
Good job. Thank you. Okay, just a quick admin note here. I guess they ran out of coffee. It's now been replenished. So welcome to have coffee out on the patio. Our next speaker is from Intel, Steve Undy. Actually, he presented, was it 92? PA RISC when he worked at HP. He now works at Intel. He has for a while now. And he's going to talk about Poulson, which is the next generation Itanium. He's the lead architect for Poulson. He's worked on several generations of Itanium at both HP and Intel, 7 generations of PA RISC at HP. He has a master's degree from Purdue and a bachelor's from University of Michigan. Steve?
Thanks, Brian. So I'm going to talk to you today about Intel's first 8-core Itanium processor, codename Poulson. It's implemented in Intel's 32-nanometer process. The goals of my talk today are to describe our probably the biggest change to the Itanium design in a while, which is a new Itanium core microarchitecture and a new Uncore microarchitecture to go with that. If nothing else, I'd like to demonstrate Intel's pretty large investment in Itanium to focus on power, performance, and reliability. Okay, well, this is our legal disclaimer slide. So I'd like to introduce Intel's latest legal disclaimer technology that's Itanium powered that results in 50% fewer legal disclaimer slides than our competition. So in this talk, I'm going to describe the design space that we're targeting Poulson into. I'm going to cover an overview of the Poulson processor and then go into more detail into the Poulson Core. I'm going to talk to you about the various levels of parallelism that we've addressed with Poulson. Then I'm going to talk about reliability, availability, and serviceability, a near and dear subject to the mission-critical space. I'm then going to discuss the power challenges we faced on Poulson and how we overcame them. And finally, if all goes well, I'll stop talking. Our design space is what Intel terms the mission-critical market segment. What is mission-critical? Well, clearly it's performance. Both single-thread and multi-thread or throughput performance are very important. Our goal for Poulson was to achieve at least a 2x speed up over the prior generation of Itanium processor. But it's not just performance, it's also scalability. The Poulson design must be robust enough to be able to scale from a small number of processors to systems that contain very large numbers of processors. Specifically, it has to support an 8-socket configuration that is glueless, and then be able to scale up larger beyond that using system chips provided by our OEM partners. Reliability is incredibly important to compete in the mission-critical space. The hardware has to be able to provide large levels of redundancy and error correction. And it has to do this in an integrated fashion with software, firmware, and the OS all combining together to provide that reliability to the end user. Finally, Poulson has to be compatible with the Itanium 9300 processor series. This is the Tukwila chip, which was the last generation of Itanium. Both Tukwila and Poulson fit into this, the same platform and share a lot of those platform ingredients with the Xeon E7 processor. So this compatibility requirement in many ways formed one of the power challenges of Poulson. So moving on to an overview of the Poulson processor as a whole, this slide compares Poulson to Tukwila. So Poulson is in a 32-nanometer process, as I mentioned, 3.1 billion transistors. So more transistors in a smaller area and actually with a lower power dissipation. It's got 8 cores, as I mentioned. Our last level cache size is increased from 24 megabytes up to 32 megabytes of last level cache. Now, while our number of quick path links hasn't changed between Tukwila and Poulson, we have increased its bandwidth from 4.8 to 6.4 gigatransfers per second, as did the SMI link, which is our high-speed link to DRAM. Here's a chip plot of Poulson. Our 8 Itanium cores are arranged around the outside. Just inboard of those are our last level cache blocks, as I mentioned, implementing 32 megabytes. These blocks are actually segmented into 8 slices associated with each core. Here are our full 4-width and 2 half-width QPI links arranged on the top and bottom. In the middle is our directory cache and our system logic, mainly composed of our router and our 2 integrated memory controllers and our SMI links complete the design. So this is just a quick example of how you would build a glueless 8-socket Poulson system. This basically allows you to interconnect 64 Poulson cores without the need of any OEM glue logic. So drilling down into the Poulson Core, this slide compares the Poulson Core to the Tukwila Core. With roughly the same number of devices, it takes up about less than a third of the area. Now, I unfortunately cannot disclose today what our core power is or what our core frequency is. But in order to provide some motivation into why we undertook such a radical redesign of the Poulson microarchitecture, I'm going to compare Poulson to a hypothetical last generation Tukwila design that's been forward ported into the same 32 nanometer process as Poulson. So comparing Poulson to this hypothetical design, a design representing no microarchitectural changes, Poulson uses 40% of the power and runs at least 20% faster. We've addressed multi-threading on Poulson, so we have more facilities for multi-threading on Poulson. We've widened our instruction pipeline. We've made a substantial change to our execution pipeline, going from a global stall-based pipeline to a replay-based pipeline to resolve pipeline hazards. Our physical register file for the integer register file, the number of the registers has increased from 144 registers to 185 registers. Along with that, we've increased the portedness of our register files. And for both the floating point and integer register files, we have better error handling. So this represents basically an all-new Itanium core. I'd like to point out that we made this change. We undertook the substantial re-microarchitecting of the Itanium core, not just for our 32 nanometer process. We plan and are actually in the process of porting this new microarchitecture into future generations as well. So along with a new microarchitecture, Poulson implements, and we extended the Itanium instruction set to add 8 new instructions. So first is a set of integer instructions, the first 2 being integer multiplies. These integer multiplies execute in our integer unit rather than our floating point unit to save latency of moving data back and forth between the integer and floating point units when you have an application that's mostly integer based. We also have added a count leading 0 instruction, which is very useful for crypto code. We've extended our control of software control over our threading capabilities. We've substantially expanded the Itanium architecture to provide a better ability for software to communicate hints to the hardware for data operations. And we've also added or extended our software prefetch capability by adding a counted LFetch, which allows moving multiple blocks of data into the data cache. As I mentioned, Poulson addresses parallelism on many different levels, and I'm going to talk about 4 different levels today: instruction level parallelism, memory parallelism, thread parallelism, and multi-core parallelism. All of this parallelism is exposed to software to be able to be under very fine-grained control. So the first aspect of instruction parallelism is the pipelining on Poulson. Poulson has 3 independent pipelines. The first pipeline is our front-end pipeline that's responsible for fetching instructions. It's got 4 stages: address generation, array access, a little bit of decode, and register rename. Register rename allows 128 logical registers as specified by the instruction set to map into 185 physical registers. The front-end pipeline feeds into the main pipeline, And the main pipeline is broken down into 7 pipe stages. The main pipeline is where we actually execute instructions. It's got an instruction buffer and a dispersal logic. It's got decode, register read, execution, detect, and a couple stages of write back. So this is where a lot of the redesign effort on Poulson went into. This is no longer a global stall-based pipeline. It is a replay-based pipeline, so any register hazards would cause a replay back to the instruction buffer. And in fact, that stage is the only stage now that stalls in the main pipeline where we would hold instructions until those hazards are released. And finally, the main pipeline feeds into our mid-level data cache pipeline. All of 3 of these pipelines are independently threaded. That is, each one could be working on a different thread from the other. And so this provides concurrency because of these 3 independent pipelines, all separated by decoupling buffers. The next form of instruction parallelism I'm going to talk to you about is basically, literally, the number of instructions that can flow down each pipeline in parallel. Front-end pipeline is 32 bytes wide, can fetch 6 instructions per cycle. These 6 instructions are dumped into a 96-entry instruction buffer that is broken up into 6 logical queues. The backend will read instructions out of these queues and then feed them into 6 different execution pipelines. So every cycle, we can execute 2 memory instructions, 2 integer instructions, 2 ALU instructions, 2 floating point instructions, 3 branch instructions, and a no-op. The algorithm and the policies by which the front end disperses instructions into these logical queues and the policies by which the back end pulls ready instructions out of those queues is completely exposed to the compilers. So we have a 12-wide issue machine in the back end. Now you could ask, why do you have 12-wide issue back end when the front end is only 6-wide? And the reason for that is because the back-end pipeline is obviously subject to hazard conditions, which can result in bubbles. By being 12-wide allows us to essentially catch up when those hazards are released, and thus achieving a much higher instruction per cycle count on average. Another form of parallelism is memory parallelism. We use this to avoid hazards by executing hardware and software prefetch operations in parallel with other operations. To control this behavior, we've expanded our software hint mechanisms. And it provides compilers the ability to have fine-grained control over the allocation policies into our caches, speculation policies, and prefetch policies. As I mentioned, we've also added a new multi-line software prefetch instruction. Itanium has facilities for control and data speculation. Poulson has taken steps to reduce the cost of that speculation, making it less hazardous for a compiler to insert these speculative load operations. Specifically, Poulson will detect conditions where a speculative load might start taking up too many resources and will spontaneously defer that load. And that deferred load can be transformed into a prefetch into the cache or TLB. Poulson also includes new hardware prefetchers, both into the first-level data cache and into the mid-level data cache. These hardware prefetchers are adaptive based on the missed patterns it sees in those cache structures in order to conserve bandwidth. Finally, Poulson reduces the number of data hazards by expanding the number of store-to-consumer bypasses in both first-level and mid-level data cache. And we've also increased the bandwidth and reduced the latency of cache line transfers between the mid-level and first-level data cache. So hopefully all this together results in fewer pipeline bottlenecks. Another aspect to memory parallelism is how many outstanding memory operations can the processor handle concurrently. So we've increased the number of pending memory operations in each core. Our ring cache, as I mentioned, is actually composed of 8 independent last level cache slices with their own pipelines and controllers. Associated with that, when we have a last level cache miss, we have 2 independent agents that are capable of forming quick path transactions in order to resolve those last level cache misses. As I mentioned, our quick path link bandwidth has been increased to 6.4 gigatransfers per second. And we've made substantial memory subsystem tweaks as well. Our home agent's queue sizes have increased. We've modified our memory controller algorithms to focus on both performance and power efficiency. And again, our SMI link to our DRAMs have also increased to 6.4 gigatransfers per second. All of this results in better queuing and bandwidth. So another important aspect of parallelism is thread parallelism. We've spent a lot of time fine-tuning multi-threading on Poulson. Biggest change is the fact that our front-end and back-end pipelines are on separate domains, something we call dual domain multi-threading. And each pipeline has its own thread-specific switch mechanism associated with it. In addition to that, we've looked at a lot of the resources that the threads use and moved them from being shared between threads to thread-specific. The basic example of that is our 96 entry instruction buffer that's actually got 2 copies, 1 per thread. And this works well with our dual domain multi-threading because now our front-end pipeline can focus on keeping those instruction buffers for each thread as full as possible so that when the back-end pipeline switches, there will always be instructions for it to execute in the instruction buffer and doesn't have to go all the way back through the instruction fetch. Our data TLBs used to be shared between threads, and now we have separate copies per thread that's effectively double the size of our first and second level data TLBs. And our hardware page walker has been redesigned to allow concurrent access for both threads on page walks. As I mentioned, we have instructions to help control our thread switch algorithms. Specifically, we have those instructions signal the priority that the hardware should attach to the threads. And we spent a lot of attention on thread fairness. So we've added hardware to identify unfair behavior between the threads. We measure instruction retirement rates and data cache resource usages. And then we've modified the hardware to react to the conditions when thread unfairness has been identified by biasing towards the victimized thread. All of this results in better throughput because we can execute each thread more quickly. So finally, the most obvious part of multi-core parallelism is what I call multi-core, multi-socket parallelism. We have 8 cores talking to 8 last level cache slices via high bandwidth, 700 gigabytes per second ring interface. And obviously, if you want to have good multi-socket scaling, you need to be able to get off the socket quickly. And so to that end, to the ring, we have attached to the ring, we have a 10-port router, which gets us to our quick path links, providing 128 gigabytes per second of aggregate bandwidth. So one of the key aspects of being mission critical is our reliability, availability, and serviceability story. This is one of the big motivators for going to a replay-based pipeline. So by using a replay-based pipeline, that gives us more time to detect errors and then be able to recover from those errors via replay before any corrupted state has been committed. We've added additional hardware for error detection and correction in the arrays, such as the mid-level instruction data, our last level tags, and our directory caches. We have single error correction, double error detection codes. Our last level cache has double error correction, triple error detection codes, and our register files have single error correction, double error detection codes. Our floating point unit has residue arithmetic for detecting transient errors. And many key paths on the chip are protected with end-to-end coverage. As I mentioned, focusing on the entire stack of hardware, firmware, and software is key to delivering reliability to the end user. And to that end, we've spent a lot of time re-architecting our entire air architecture on Poulson. OK, the final major design point is our focus on power. This is important because we've doubled the number of cores per socket and increased the frequency, but actually lowered our power envelope. One of the key ways we achieve this is, again, through our replay-based pipeline. This has enabled fully gated clocks and removed the need for power-wasting global stalls that also have a deleterious effect on clock frequency. With our aggressive clock gating that we've pursued across the processor, we've seen substantial reductions in idle, typical, and maximum power scenarios. We've redesigned our floating point unit to remove dynamic logic. We've used an automated low leakage FET algorithm that allows us to reduce leakage power on the die without affecting clock speed. And Poulson also implements a digital power estimation similar to Tukwila by measuring and weighting key architectural or microarchitectural state. But this goes beyond that on Poulson to actually look at data patterns on key buses. And this reduces our estimation error, power estimation error, from 35% down to 2%, especially over the smaller time windows that Poulson uses for estimation. All of this results in a 60% TDP, 70% idle dynamic switching capacitance reduction over our hypothetical process scale Tukwila. So what's the status of Poulson? We're well into our post-silicon validation cycle. It's booted and is being tested today on multiple operating systems in multiple system topologies. And we're on track for 2012 shipments. In addition, the Kitson design, which is the follow-on to Poulson, is also being actively worked on. I should know that's actually my day job. So in conclusion, Poulson represents an all-new core design. It's 12-wide issue. It's got what we call dual-domain multi-threading. It's got additional instructions and better ability for software to control the fine-grained behavior of that hardware. It's got a replay-based pipeline that reaps benefits in frequency, power, and fault tolerance. And the net result is our core power efficiency is at least 3 times better than Tukwila's. So in other words, we've redesigned the core, and we've done it in such a way that it will not only scale to this generation, but future generations as well. Poulson also is our first ring-based Itanium design, featuring large last-level caches, interconnected by a high-bandwidth ring and link interface. And it's got outstanding data reliability. We've added more and better error detection logic, better error recovery, and even more importantly, we have a fully integrated hardware, firmware, and software stack to deliver that reliability to the end user. And that concludes my presentation today, and I'll take questions now.
Nathan Brookwood, Insight 64. Given the software visible changes you've made in the architecture here, in particular the issue with, and given that you expose so much of this to the software, what implications are there for applications moving to Poulson? Will they need to be recompiled in order to take advantage of these new features, or can you just move the binaries over without any effort?
So that 2x performance improvement that we've targeted is assuming no recompilation. In other words, legacy binaries will see a 2x increase in performance on Poulson. However, there is upside to that if you recompile. And so that's about all I can say. I'm not allowed to talk about specific performance at this point.
And if you don't recompile, you still will still get some benefit from the extra width in terms of issue? Absolutely.
In fact, Intel has been, okay, I have to be careful what I say. Yes, we believe that existing binaries will be able to take advantage of our new pipeline.
Thank you.
Paul Lowenstein, Oracle. Can you clarify the last level cache structure? Is the cache per core? Is it with?
So it is physically. There's the cache and the CPU, the core and the LLC slice are essentially associated with each other physically, but logically, requests can go to any of the slices, any of the cache slices. It's
and allocation is always in its own local one, or is it?
No, there's a hashing algorithm to go from a physical address.
So it's address sliced.
Yes.
Okay. Thanks.
Hi, Charlie Demergen, Semi-Accurate. The question that, well, I think everyone wants to ask is, you compared Poulson Core to a Tukwila Core. How does it, for power efficiency, performance, et cetera, how does it compare to a comparable Xeon Core?
In order to be able to do that, I would have to talk about specific performance levels, and I'm not really at liberty to discuss it. I'd like my paycheck, and I'd like to keep it.
Okay.
Go ahead. James Stringelli from Rambus. I noticed that you have increased the amount of error correction capability in the last level cache and the register files. Is this motivated by process scaling, error rate increases? And will this continue? Will we see more and more error correction as time goes on?
I hesitate to speculate about the future, but one of our motivating factors is that our system partners want to see the same level of data reliability measured at a socket level. And so we've doubled the number of cores going into a socket. And so we more or less were forced to make each core even more data resilient, error resilient than before.
Okay, thank you.
Mm-hmm.
Ramin Shirani from Aquantia. You mentioned removal of dynamic logic from the floating point unit. What were the specific problems that led to that decision?
Well, our feeling is the dynamic logic was using too much power given the benefit it was providing. So we redesigned it to be fully static.
Leakage was a concern?
I am not a circuit designer. I'm a microarchitect, but I believe so, yes.
Okay, thank you.
John Delaney, you kind of danced around the issue, so I'm going to see if we can call it out. Is Poulson so awesome that you think it'll make Oracle reverse its decision not to support Itanium?
Are you expecting a serious answer to that question?
I'm expecting you to dance.
I am a lowly engineer, not a marketing person, so I'm not really sure I can answer that. But Oracle's going to do what Oracle wants to do.
Hi, I'm John Wharton. This may come across as being rude, and I don't mean to, because I really don't know enough to understand all this. But there have been presentations. You started shipping Itanium, I think, about 10 years ago, and there have been talks at Hot Chips for probably 14, 15 years. And it's a technology conference, so it's good to learn about the technology, and that's fascinating. But what can you say about the business success, whether this has paid for itself, whether you expect it to? There was a Hollywood film mogul in the 40s who said something about when he's looking at a movie, if nothing happens in the first 10 minutes, nothing's going to happen. The x86 products have gone through, I mean, they certainly have a lot more visibility still, long after Itanium first started shipping. So can you say anything about the volumes or the applications or what's going to happen other than on a technology side?
Again, I'm not a marketing person. I can say that Intel makes a profit on Itanium sales and that our system partners wouldn't be using Itaniums if it didn't actually provide them a great deal of value. Beyond that, no, I can't say anything.
Okay. Thank you. Sorry for the rudeness.
Thanks, Steve. Thank you, Steve. Give Steve a round of applause. Okay, so that was our second paper. Our third paper actually is from Oracle, coincidentally. And today they're going to disclose their T4 processor. It's being presented by two gentlemen, Robert Golla and Paul Jordan. Robert's a senior hardware architect at Oracle and Sun for 24 years of microprocessor experience. Most recently worked on the T4, but has also worked on the N2 prior to that. Has a history of microprocessors with Sun, Motorola, and IBM's various PowerPCs and power processors. He has a BSEE from University of Houston, an MSCE from University of Texas. The second gentleman is Paul Jordan. He's also a senior principal hardware engineer at Oracle with 20 years experience. Let's see, he worked on the T4 and the commit and exception processing logic. He also worked on the N2 with Robert. And Power 4, 620, Power 2, all these processors at IBM, and he has a BSEE from Rice. So please welcome these gentlemen and the T4.
All right, thanks, Brian. Today, Paul and I will be talking about T4, which is a highly threaded server on a chip with native support for heterogeneous computing. Okay, so as for the agenda for today's talk, I will be giving a general overview of the T4 processor, and then I'm going to be talking about T4's core, which we call S3, and then I will be talking about the relative performance of T4 versus T3. Paul Jordan will discuss how we did dynamic threading on the S3 core. He will discuss S3's crypto, and finally, Paul is going to wrap up with a summary of the T4 processor. One of the things we wanted to do with the T4 processor was to optimize the software and hardware stack in order to run Oracle applications as efficiently as possible. And to facilitate this, we added a bunch of new instructions to the Spark instruction set. These instructions included user-level crypto instructions, a new pause instruction, and a new fuse compare branch instruction. Another thing we wanted to do with T4 was to give it a much broader performance envelope than what we previously had with our T3 server processor. Compared to T3, T4 has much better single-thread performance. It has significantly better throughput per strand performance, and it has improved overall core crypto performance. In terms of compatibility, any application written for T3 will run on T4 without modification. And in addition, applications will scale on T4 the same or better as they did on T3. And lastly, T4 has enhanced reliability. T4 protects more hardware structures and has more hardware correctable RAS errors than T3 did. This is a die photo of the T4. And for T4, we essentially started with T3's die. And T3 had 16 Niagara 2 cores. So for T4, we replaced those 16 Niagara 2 cores with 8 new S3 cores. And you can see them up here. There's 4 on top and 4 on the bottom. In addition, we had to replace the L2 and the crossbar from T3 with a new L3 and a new crossbar designed to run as the same frequency of the core. So the crossbar is right there in the center, and there's an L3 above and below. Pretty much everything else we leveraged from T3 unchanged. T4's L3 is 4 megabytes. It has 8 banks, and it's 16-way set associative. Since we leverage the same die, like T3, we have 2 dual-channel DDR3 1066 memory controllers, 2 PCI Express x8 2.0 ports, and 2 10 gigabit Ethernet ports. T4 is manufactured by TSMC in a 40 nanometer process and has approximately 855 million transistors. So at some level, the S3 core is going to be a foundation core for Oracle. It's currently used in the T4 processor, and it's also going to be used for future Oracle server processors. It's a brand new from-scratch design. It's fully out of order, and it's dual issue. S3 is dynamically threaded. Essentially, all of the resources on the core are dynamically shared between all of the threads in a fine-grained manner. Dynamic threading can improve the overall performance on heterogeneous workloads involving low IPC threads running with high IPC threads. And one thing I want to note, when we say heterogeneous in this talk, we're talking about workloads and not about building blocks. I've noticed that a lot in the presentations. S3 has a balanced pipeline design. In terms of single thread performance, S3 has approximately 5 times S2's SpecInt 2006 performance and approximately 7 times S2's SpecFP 2006 performance. In terms of throughput performance, we have approximately 2x S2's per strand performance. S3 is a high-frequency deep pipeline design. It has a 16-stage integer pipe, and it currently runs at 3 gigahertz. So for S3, we have extensive branch predictors to help mitigate the cost of branch mispredicts. All of the threads on the core share these branch predictors. For direction prediction, we chose a perceptron predictor. Perceptron has very good branch prediction accuracies for a wide range of applications. A little bit more importantly, we also found that perceptron behaves very well for multi-threaded workloads. And lastly, we found that perceptron was relatively cheap to implement. S3 has a return stack to predict subroutine return addresses. It has far and indirect target predictors, and it has a small, fully associative branch target cache. The branch target cache remembers the most recently taken branches, the targets of those branches, and if a branch hits the branch target cache, it incurs a 1-cycle taken branch penalty. S3 has new user-level crypto instructions. These instructions can significantly reduce the overhead associated with the encryption and decryption of data, especially for small packet sizes. Because these are user-level instructions, they can easily be threaded. And by threading crypto instructions, we end up improving the overall core crypto performance. S3 has a new pause instruction. The pause instruction can be used to pause a thread for a fixed number of cycles. Software can use this instruction to implement various back-off schemes involving spin lock constructs. It can also be used to implement lightweight sleep constructs. When a thread is paused, it frees up all of its allocated resources, allowing other threads to make use of these resources for execution. S3 has a fuse compare branch instruction. The compiler can use the compare branch instruction to replace 2 discrete instructions, a compare and a conditional branch, with a single compare branch instruction. For certain applications, this can reduce the overall path length by over 10%. S3 has an instruction cache sequential line prefetcher. Up to 16 iCache prefetches can be outstanding at a time on S3. It has a data cache stride-based prefetcher. Up to 24 data cache prefetches can be outstanding at a time. S3 has a 16 kilobyte 4-way level 1 instruction cache. It also has a 16 kilobyte 4-way level 1 data cache. And lastly, S3 has a 128 kilobyte 8-way unified L2 cache, and it has 1 of these per core. This is a block diagram of the S3 core. And I'm going to pretty much walk you through it to kind of give you an overview of the core. So each cycle, the fetch unit chooses 1 out of 8 threads to fetch from the iCache and it uses the least recently fetched algorithm. It takes 3 cycles to fetch instructions from the cache, and up to 4 instructions can be fetched each cycle and written into the instruction buffers at commit. At select, pardon me. At select, there are 8 instruction buffers, 1 per thread. Each instruction buffer has 32 entries. The select unit uses a least recently selected algorithm to choose which instruction buffer to pick to send down the pipe, and up to 2 instructions can be selected each cycle. Instructions sent down the pipe by select, it takes 2 cycles to fully decode them by the decode unit, and slot assignments are done by the decode unit. On S3, there are essentially 2 slots, slot 0 and slot 1. Slot 0 executes all load store operations, and slot 1 executes all branch, floating point, and crypto operations. AOU operations can be executed on either slot. The rename unit takes 3 cycles to rename the instructions and write them into the pick queue. S4 has a 40-entry unified pick queue. All micro-ops go through the unified pick queue. The pick queue picks the oldest ready to execute instruction per slot each cycle. It takes 4 cycles on S3 to read the integer register file, the floating point register file, and the working register file. On S3, we support 8 Spark register windows per thread. This translates to 160 integer registers per thread. And with 8 threads, this gives us a total of 1,280 integer registers that are actually in the integer register file. The floating point register file has 256 entries, or 32 entries per thread, and the working register file has a total of 128 entries. Results are written to the working register file before they are actually committed. S3 has 2 ALUs. They are essentially symmetric. They forward to themselves and each other in a single cycle. The branch unit executes all branches and also determines all branch mispredicts. The floating point unit executes all floating point operations, and on S3, it also executes integer multiplies and divides. The crypto unit executes all new user-level crypto instructions. S3's commit unit can commit up to 2 instructions each cycle using a least recently committed algorithm. On S3, we can have 128 instructions in flight from select to commit. S3's performance monitor unit keeps track of various performance-related events using counters. Each thread has 4 32-bit configurable performance counters. The load store unit on S3 executes all load store operations. The level 1 data cache is right through. Loads allocate in the data cache, stores do not. And the load store unit can have up to 32 outstanding data cache misses at a time. S3 has a 64-entry fully associative level 1 instruction TLB. It has a 128-entry fully associative level 1 data TLB. The memory management unit on S3 hardware table walks L1 level 1 TLB misses. Up to 8 instruction and 16 data TLB misses can be outstanding at a time. And lastly, S3 has a private 128 kilobyte L2, and the L2 is right back. This is a pipeline diagram of the S3 core. S3 has a 16-stage integer pipe. The crypto pipeline has a 3-cycle latency for crypto operations forwarding to other crypto operations. The load pipeline has a 5-cycle load use latency. And the floating point pipeline has an 11-cycle floating point latency. For crypto operations that forward to non-crypto operations, the latency is also 11 cycles. On S3, integer results that forward to integer dependence occur in the I4 pipe stage, and floating point results that forward to floating point dependence occur in the execute pipe stage. By design, there are very few stall points in this pipeline. The only places this pipe can stall is before the fetch pipe, before the F1 pipe stage, at select, at pick, and at write back or commit. Pipeline stalls are costly when you have a heavily threaded pipeline such as S3's. One reason they're costly is every time you stall, you have to provide some amount of thread buffering for each thread. Another reason they're costly is every time you stall, you have to provide some amount of thread arbitration. This is a threaded view of the S3 core pipeline. In this diagram, each color represents a different thread. I realize you have a black and white handout, so sorry about that. But for the F1 to F3 pipe stages, the threads are vertically threaded. There's only one thread per pipe stage. At select, each thread has a 32-entry instruction buffer. However, select can only choose one of these to send down the pipe each cycle. From D1 to R3, once again, only one thread per pipe stage. At pick, any number of threads can be present. The pick queue is thread agnostic. It simply picks the oldest ready to execute instruction each cycle. From pick to commit, multiple threads can be present per pipe stage. And lastly, at commit, only one thread can be present per pipe stage. The commit unit can only commit one thread per cycle. This is a chart of the relative performance of T4 versus T1, T2, and T3. Kind of gives you a history of what led up to T4. T1 used the S1 or Niagara 1 core and had 32 threads. T2 and T3 used the Niagara 2 or S2 core. T2 had 64 threads. T3 had 128 threads. And T4 uses the new S3 core for a total of 64 threads. The x-axis represents multi-thread performance, and the y-axis represents single-thread performance. So as you can see from this chart, we have significantly better single-thread performance versus T3, and we also have much better throughput performance per strand. T4 has 64 threads, and T3 has 128 threads. And lastly, we have a broader performance envelope for this processor on this chart. This chart shows the relative performance of T4 versus T3 for SpecInt 2006 and SpecFP 2006. For SpecInt 2006, T4's performance is approximately 5 times T3's. And for SpecFP 2006, the performance is approximately 7 times T3's. The main reasons for this improvement in single-thread performance for T4 over T3 is that T4 is dual issue, it's out of order, it runs at 3 gigahertz, it has extensive branch prediction, it has a private L2, and it has a data cache prefetcher. With that, I'll turn over to Paul. There you go.
Many of the resources on the S3 core are shared between threads. When we started to design the S3 core, we had to decide how we were going to deal with the sharing of resources. And we thought about several different scenarios. One that we thought about is the situation of heterogeneous workloads. That is, you may have some threads that could achieve a high IPC if given enough resource, and at the same time you may be running other threads that are going to run at a low IPC regardless of how much resource you give them. We also thought about application scaling, particularly per Amdahl's law. We also thought about applications that may have sections where they're going to run at a low IPC and then transition to a section where it could achieve a high IPC if given enough resource again, and then transition back to a low IPC section. So when we thought about these various scenarios, we realized that static resource allocation really wasn't going to give us the performance we were looking for. For example, if you had 8 threads running and you were to divide the pick queue into 8 separate sections and assign each section to a thread, we really weren't going to get very good performance. So instead, we went with a dynamic resource allocation scheme. We found that it was better for heterogeneous workloads, and we found that it improved overall application scaling, especially per Amdahl's law. We implemented this in a fine-grained manner. That is, most of the resources are allocated 1 entry at a time to each of the threads. And the way that we did this, we did it with no synchronization required. That is, if you add or delete threads, or you have an application that's transitioning from low IPC to high IPC or back again, all this resource allocation happens without any hardware or software synchronization required. When you do dynamic resource allocation, though, you can create the problem of a thread hog. And a thread hog is really indicative of inefficient resource allocation. Its definition is a thread which fails to release its shared resources in a timely fashion. So to deal with this, we have several different mitigation techniques that we've implemented on the core. The first is using watermarks. Watermarks really boils down to looking at the number of entries that are already allocated to make decisions about future allocation. So for each resource, we define a high and a low watermark. And as a thread allocates, if it reaches the high watermark point, we assert a stall so that that thread can no longer allocate that particular resource. And that stall remains in place until the thread deallocates enough entries to achieve the low watermark, at which point we release the stall and the thread's able to get more of that resource again. The second technique looks at the rate of deallocation to control the rate of allocation. We use this technique on the pick queue being the most critical shared resource on the S3 core. And for the pick queue, we expect a thread to deallocate its entries in a timely fashion. In the event that it doesn't do this, we consider it a pick queue thread hog. For pick queue thread hogs, we reduce the maximum rate of allocation of pick queue entries to that thread. If that thread continues to remain a pick queue thread hog, that is, it continues to fail to release entries in a timely fashion, then we further reduce the rate of allocation. Eventually, that thread will start to deallocate in a timely fashion, and at that point, we'll open up and we'll allow the rate to increase again. The final category I'm going to discuss involves using flushes. We use this technique when we detect that a thread has reached a condition that it's not going to make forward progress in a significant amount of time, and that it would be more efficient for that thread to release all of its shared resources so that the other threads could take advantage of them. So for example, if you have a load and the load misses the L3, we know that that L3 miss is going to take a significant amount of time to be serviced, so we go ahead and we flush that thread. By flushing that thread, we release all of the shared resources allocated to that thread. Other threads can take advantage of them at that time. Our load store timeout mechanism is designed to catch conditions that are not caught by any of our other mitigation techniques. For example, if you have a load and the load itself raws against a prior store, and the store missed the L3, we don't get an L3 miss indication on the load. So what we do is, anytime we have a load or store that becomes the oldest in the machine for that thread, and it has not committed for a certain number of cycles, we go ahead and we flush that thread, again under the assumption that this is going to take a period of time to resolve the condition that led to it not being able to commit. Similarly, if we have an I/O access that reaches commit and it is not ready to commit, we go ahead and we flush the thread. Moving on to an overview of the cryptographic unit, our cryptographic unit is now programmed via user instructions, and we divide these instructions into two sets. Our in-pipe set supports that 3-cycle internal latency that Robert showed you, and that includes AES, DES, Kasumi, Camilla, and CRC. Our out-of-pipe set has a long latency. What this means is that while these operations are executing, no other instructions can execute for that thread. And this set includes MD5, SHA, multiple precision multiply, Montgomery multiply, and Montgomery square. Our cryptographic multiplies have a separate state machine that asserts stalls back to the pick queue to create holes to get access to the multiplier inside the floating point and graphics unit. And we have a fairness heuristic to basically ensure fairness between cryptographic multiplies and non-cryptographic multiplies. This is a block diagram of the cryptographic unit. You can see the MA controller that I discussed interfaces directly to the FGU multiplier. You can see that we have a full bypass between our 3-cycle latency engines. You can also see that that bypass provides a single result bus and 3 operand buses to our architected register files, our IRF and FRF within the execution unit. Those buses are also shared between the cryptographic unit and the floating point and graphics unit. And then finally, to get access to the architected register files, we just use normal loads and stores through the load store unit. This slide shows relative core-to-core performance for our cryptographic functions for T4 versus T3. You can see our AES performance is improved by a factor of 2.5. Our CRC performance is improved by a factor of 3.5. And the balance of the others, RSA, MD5, and SHA, have improved by a factor of 1.5 to 2. This slide actually shows raw hardware performance, and so is indicative of large packet support. However, if we had the graph for small packets, you'd find that T4 has an even greater relative benefit. The reasons for that are that the T3 core's cryptographic unit was really a coprocessor, and so you had to go through a hypervisor software layer to get to it. And then secondly, with those 3-cycle latency operations, it's possible on T4 to have multiple threads doing cryptographic functions concurrently. So in summary, T4 is the next generation processor for Oracle servers, and the S3 core is the next foundation core for a line of Oracle servers starting with T4. We've improved per-thread throughput performance by a factor of 2, and we've improved single-thread performance by a factor of 5 to 7. By implementing dynamic threading, we've got a model that's better performance for heterogeneous workloads, that is having low IPC and high IPC threads running together. And we've improved overall application scaling per Amdahl's law. We've maintained our tradition of excellent overall cryptographic performance, and with our user instruction interface, particularly for small packets, we've enabled transparent encryption across the Oracle software stack. Thank you very much.
So I guess now we'll open it for questions.
I think we have a couple of minutes for questions. Then we all, I'm sure, want to get out to lunch.
But Todd Besnick, Quantum. This is designed to be used to run Oracle's applications. Why did we only see spec benchmarks? Was there a thought to doing that?
This is not really, there was a very limited amount of data that we could publish here at Hot Chips. This is not the announcement of the T4 processor. It's some sense sort of the disclosure. It's kind of strange in that sense.
No, that's
so,
good.
Yeah, we couldn't really show the other Oracle benchmarks.
Okay.
Hi, Eddie Gornish, Hewlett Packard. I actually had a question about the spec CPU slide too. Were those speed numbers or rate numbers?
Those are ratio numbers. Those were single thread numbers.
Okay, can you say anything about the spec CPU rate performance, let's say T4 to T3 socket per socket?
I cannot.
Okay. And just another clarification, a question about the...
when the part is announced, all those will be, be part of the announcement, I would think.
Of course, sure. About the iCache and dcache data prefetchers. You may have said this, I may have missed it. Are those from L2 to L1, L3 to L2, memory to L3? At what level are they implemented?
The data cache, I believe, lifts up to the L1. Yeah. And the iCache, obviously, it's lifting up to the L1 as well.
Okay,
so
thanks.
Both lifting to the L1.
Thank you.
Rick Merritt from EE Times. A short and a long question, if I may. Short question, what's the status of the T4?
T4 is well along. It's been running now for it's been running all this year, so it's well along.
And the longer question, when you were part of Sun Microsystems, you were pretty famous for the philosophy of maxing out the number of threads, kind of leading the industry in that way. I wonder if you could describe at all how your design philosophy has changed at all under Oracle.
So under Oracle, kind of amazingly, our direction has remained the same as what it was under Sun for the most part. We still see a significant benefit from going from 8 threads to 4 threads on commercial applications like databases. So we still see a benefit there. I think all of this work was already well underway, and you can probably tell that we didn't just crank this out in 6 months or something. So all of this was well underway, and we just continued it. We were looking to get better single thread performance. To give you a little longer answer, we were looking at how to do, we looked at heterogeneous building blocks. And while we were doing that effort, we were looking at doing very high single thread. we decided to make a single core. It'd be more efficient for us to have a single core that could do well on both. So that's the way I still think we lead in threads. I think, you know, at some level, this part is a little bit of a tick-tock part. You notice it's a new core, but on an existing process with an existing SoC. So, you know, I think in the future, you know, I think we lead currently in threads, and that will continue, I think, in the future.
Thanks.
Bill Rash, Intel Corporation. How would you compare the memory capabilities in terms of bandwidth and capacity of the T4 versus the T3?
I would say since it's the same die, the memory bandwidths are identical with the T3. If that's the question for the memory bandwidth, it's the same die, so it's the same IOs. So it's the same.
It's the same, okay.
Yes.
Thank you.
Stefan Meyer with Apple. Just two technical questions. I saw you had a 5-cycle load to use, and I was wondering if you could, with a 16K data cache, which seemed rather long, I was wondering if you could say anything about what led to that design decision.
So amazingly, for a single thread, we can get so much overlap out of that 40-entry PIC queue. We're very efficient in that PIC queue. And we deallocate an arbitrary number of things from that PIC queue each cycle. And for certain integer small loops, you can run out of the level 2 data cache and see a very small degradation because we're able to hide enough of that. Now, having said that, you can certainly write applications like memory pointers, and you can get a direct performance correlation to the load use latency. So we didn't decrease it because there wasn't, especially when you go to multi-thread, you know, things you do for single thread don't translate over to throughput necessarily. So that was a comfortable design point for us. And remember, we're running at 3 gigahertz now, so we were, you know, moving up that scale as well as in a foundry. You know, we are a fabless semiconductor company. So we're comfortable with 5-cycle load use. I wouldn't say that we wouldn't improve on that in the future, though.
All right, thanks. And one other question was just your cache hierarchy. I saw you have a 3-level hierarchy. I was wondering if you could say anything about the policy you chose in terms of inclusion, exclusion at the various levels and why.
So if you remember back to the Niagara processor family, all the stores had to go down to the last level cache for ordering. And there were ACKs back before, you know, you had to get an ACK back before you could do anything with the store. You can't maintain high-level single-thread performance with that design, so that latency had to move up. That's one thing. Secondly, load locality matters, so if you have, you know, obviously those are small. If you can reduce, it helps reduce the average load use latency. Having it nearer is another point. Okay. Even though I said we overlap a lot, which we do, but still it helps.
Right, so. And did you make your L2 and L3 inclusive or exclusive?
Oh, okay.
Yeah, we store into the L2.
Everything's inclusive to the L3.
Everything's okay.
L3 knows everything.
All right, thanks.
Yeah.
Appreciate
it. The level 1 was right through, like I said, and the level 2 was right back.
Thanks.
David Bison from Lab for Physical Sciences. What is the expected date of shipping on this?
It will be soon. No, I really, this is not an announcement, so I can't. What did the guy say? He's a lowly engineer. I'm a lowly engineer. I mean.
Secondly, on your branch prediction, you're using a perceptron. What was your inspiration for moving to that?
I would say originally, I mean, I was not the branch architect. But I would say that it was the cost of implementation, the prediction accuracies for single thread coupled with the prediction accuracies for multi-thread. All those things taken together is what led him to that choice.
And is that a standard
It is not
method,
a standard.
Single layer activation units, that type of thing?
I can't comment on the actual implementation. What I was going to say is I think it may be, I am not aware of any other perceptron branch predictors that are currently commercially available.
That are in silicon now.
Yeah, there may be, I just don't know.
Okay, with that, I want to thank the speakers.